Okay, so we are continuing now with another variant of the Kalman filter, which has been used in the context of the simultaneous localization and mapping problem. And what I want to present today is the so-called extended information filter. And today we again won't look really into the SLAM properties or how this can be used for SLAM, but introduce the information or extended information filter, which we will then use next week in order to build a SLAM system based on top of that. And this uses not the plain extended information filter as I'm going to present it here right now. The SLAM system uses a sparse variant of that and makes some approximations in order to become more efficient than the Kalman filter was doing this, or exploit some of the advantages. So the extended information filter is kind of often also called the dual filter to the extended Kalman filter, as it has the same properties in terms of the things it can estimate, but it changes the representation in which it is done. So what the extended Kalman filter was doing, it was using Gaussian distributions. And it was using Gaussian distributions, describing them with their moments, the first two moments, which is the mean and the covariance. Therefore, this form, as you may know, the Gaussian, is also called moment form. There's the mean and the covariance are called moments of the distribution, the first two moments. So we had the standard equation of the Gaussian distribution. Here, the variable x of the probability distribution minus the mean times the covariance, the power of minus 1, so inverted, and the same term over here again. However, this is not the only way to represent a Gaussian distribution. You can also represent a Gaussian distribution in the so-called canonical parameterization. Instead of using a mean and the covariance matrix, the canonical parameterization uses the so-called information matrix, which is the omega, and the so-called information vector psi. And the canonical representation is just an alternative way for representing the Gaussian distribution. So instead of estimating, so we want to transform the extended Kalman filter into an extended information filter, what we have to do is to not use the mean and the covariance matrix anymore, but using the vector psi and the vector omega. As you may expect, this should lead to exactly the same properties of the algorithm in terms of how accurate is it and what it can estimate, the assumptions it makes. This is definitely the case. The only thing is that the different steps, basically the update and the prediction step, change in terms of their complexity. So what it will turn out to be is that the prediction step, which is easy in the Kalman filter, turns out to be difficult or complex in the information filter. And the measurement update, that is more complex in the extended Kalman filter, turns out to be easy in this information filter. So this suggests that this is kind of the dual thing. You can't get everything cheap because converting between both representations is also expensive. But depending on the properties of the underlying system you're using, the information filter can be a better choice than the Kalman filter or the other way around. Okay, so let's look how does this canonical representation look like. So the matrix omega is simply the inverse of the covariance matrix. So the inverse of the covariance matrix is the information matrix. And an information matrix which is 0 means you have infinite uncertainty. You don't know anything, so you have no information. The bigger the values are in this information matrix, the more information you have about the variables, and the smaller the uncertainty, so the smaller the covariance entries of these elements are. Okay? So you're clear what the difference between both of them is? Consider the one-dimensional case when this would be just a scalar. If you have information of 0, you don't know anything, when this expresses the infinite uncertainty, because it would be 1 divided by 0. Something you can express actually in information form, having no information, which is information matrix 0, which we can't really represent in the covariance matrix because it's infinity. And but except for that, it's just one of the inverse of the other. And the information vector is actually defined psi as the inverse of the covariance matrix times the mean. It's so-called the information vector. Again, it's just a different representation. And actually both representations are complete representations, so they describe the Gaussian distribution in the same way. So you can either use the moment form, which is here, or the canonical form, which is here. You can so unless, as long as you can invert the information matrix and the covariance matrix, you can switch between these two representations just by inverting the information matrix or inverting the covariance matrix, and by multiplying either psi to the inverse of the by multiplying psi to the inverse of the information matrix, so the covariance matrix, or mean to the inverse of the covariance, namely the information matrix. So you can switch between both of them. Okay, so the question is then, how does the probability distribution in the information form or the canonical parameterization look like? Let's start from the form we know. So the probability distribution of x with the standard Gaussian in the moment form is given here. This is something you all know. The first thing we can do is actually we can multiply out the different terms we have in here. So you can say this is, so you can multiply out the individual terms so that we come up with this equation over here. So we have x sigma to the power of -1 times x, first term over here. Then we have plus the mean transpose sigma times x, which is with the 2 times, I put over here, and then the last term only covering the sigma terms over here. Okay? So if we have that form, we can actually split that up into 2 terms. So we can actually split it over here and put that into 2 expressions. So the first expression, the factor here keeps exactly the same. So there's the first term and then the second term over here. So this part goes in here and this part goes in here. Here so far? So if you look at this term, what do you see in terms of the probability distribution about the variable x is handling? Second. The first term, this term over here.
Mean is 0.
The mean is 0, that's true. The mean is there. Which variables does this term depend? So we have a probability distribution over x. Is there any x in here?
Constant.
It's a constant factor. So this term is simply a constant factor which doesn't depend on the value of x, which I put in there. Right? So only depends on this term. So I can actually move that into constant. So this whole term here is now one constant. It's expressed by this variable over here, versus independent of the variable x. So it's this function over here. And now we can simply start replacing the individual terms in here with the information matrix and the information vector. So this term, sigma to the power of inverse, was what?
Omega.
Exactly, so this is the information matrix. And here we have sigma to the power of -1 times the mean, was psi was the information vector. So we can perfectly replace that and now end up here with x transposed omega x times x transposed psi. And one of the reasons why this function sometimes preferred, or this representation is sometimes preferred over the moment representation, is that this term over here is actually a quadratic form. It's a kind of function that has certain properties that we'll also look into more detail later on in the course. Also, if you look into interpreting this as an optimization problem, then this quadratic form has certain nice properties that we're going to exploit. But that's the reason why the information form is also an attractive form for doing certain operations. So at the end, we end up having two representations. This is the canonical representation, so written in a complete form, and so we have a constant over here, and we have the moment parameterization. Okay, so let's in a similar way as we made the transition from the moment form to the information form, we can actually do exactly the same thing for the Kalman filter now. Let's start with the Kalman filter, and so as we looked into that in the beginning of the course, and then change the individual components in this Kalman filter so that we end up with the information filter. Okay. So here was the kind of plain Kalman filter algorithm, so even not the extended Kalman filter algorithm, just the plain Kalman filter algorithm. And let's see which components we need to change or how we need to change them in order to come up with a representation that works completely in the information form, not in the moment form anymore. So I want to get rid of the mean and the covariance as the input, and the input should be omega and psi. Okay. So look to the first term over here. Let's start with the covariance matrix. Let's copy that down. AT t minus 1 transpose plus RT. And I want to have omega here, right? Omega. So I need to invert the whole term here. We should have something here to the power of minus 1. AT, what else?
Inverse.
Sorry?
Inverse.
To which variable does this correspond to? Okay. Omega t minus 1 inverse AT transpose plus RT. That's it. So next, second thing was the mean was AT mu t minus 1 plus b ut, and if you don't want to have psi, so how do we have to replace that? So what was the mean? Plus ET UT. That's it. There. First step and second step, so that we end up with an information filter, which has exactly these terms here. First two steps. As I said, the input is only psi and omega. I just use my equation of psi and omega. The correction step can even do simpler. So it's more difficult if we manipulate all the matrices of the Kalman game, so we can actually look that up in a similar way. If you look to the first base filter equation, we had the base filter was a normalization constant in the update step of the measurement model times the predicted relief. And this guy we already have. We know that's a Gaussian distribution. Okay, so let's write it down in the form of the moment forming Gaussian. So this was the observation model. So we had the linear transformation of transforming x into the space of measurement. So this was the predicted measurement. So this CT, XT, and we have the uncertainty of our observations. And here we have the Gaussian distribution over the using the predicted belief from the first step. Okay, you can simply join those two terms into one big term. Just this is a product of two exponential functions. You can simply join their exponents, and now we can actually make a big multiplication, taking all those terms out. We may end up with something like this. So this, again, as we did it before, the first group all terms which are quadratic in x, so it's kind of a half times CT XT, both transposed, QT is XT, that's this term over here. Then we get a second term which is quadratic in x from this part over here, which is, where is it? This is already directly put into the canonical form over here. So that's putting in the canonical form. And then we can actually move this term, which is quadratic in x, the omega over here, and this term over there, just replacing the order. And then we can actually write that as x transposed, this big term over here, x times x transposed this term over here. Since we know we want to have that in a canonical form, the only way we achieve that is that this is the new information vector, and this the new information matrix. Which we have exactly the form minus 0.5 xt information matrix x plus x transposed times the information vector. Just by saying it's in the canonical form, so these have to be those two values we have over here. Okay, so from this term over here, we obtain the update step over here, so we don't have to compute any Kalman gain or anything. We are directly there. So it's 4 lines, 2 lines for the prediction step and 2 lines for the correction step. We are actually at the information filter value, which is this one over here. Nice, small, beautiful. Okay, we have those 2 steps. So we have the prediction step and the correction step shown over here. What are differences in the prediction step and the correction step with respect to the extended Kalman filter? If you look at the individual terms, I've derived all of them from the Kalman filter. As long as we have made no mistakes, it should be exactly the same from the quantities we are going to compute. So if you would turn the information matrix and the information vector after our transformation into the moment form, we should get exactly the same results. But what's the difference if you look to those 2 terms over here?
Well, the prediction step is obviously much more expensive because we have an inversion, and the correction step is less expensive because we don't have an inversion.
Yeah, it's actually inverse, so we have actually 2 inversions here. Okay. So this is potentially, this is the covariance matrix which has the full state space, and so we transform it, add the noise term, and then have to invert it again. 2 inversions. Potentially with a matrix covering the full state space. And here we have the same inverse. So once we have this term over this one, it's easy. And the correction step here is less critical because it doesn't involve any inversion. It simply is the product of matrices. So if you look to the Kalman filter and compare the complexity cluster of the Kalman filter, an efficient prediction step was quadratic in the number and the dimensionality of our state space in the worst of the cases. So the slant problem where we only updated a small portion of the state space, it was even more efficient, right? Because you only needed to update the part of the covariance matrix which was related to the position of the robot, so the small block, and then the cross covariance entries. So we could actually do that in the example we present in linear time. Okay, so this is quadratic, and the costly correction step, which is quadratic in n and cubic in k, which was the dimensionality of the measurement function. If you look at the information filter, there's a costly prediction step, and it's n to the power of 4. Because we need to invert the full information matrix, need to add something to it, and then invert it again. The correction step, however, was more efficient. So it was, again, quadratic in the dimensionality. Again, depending on how the control exactly looks like, we made it more efficient. And the cost of changing between both representations is actually also cubic in n. So we can't say, okay, we do the prediction step in the EKF, then we change to the information form and do the update step in the information form. The prediction in the Kalman filter, so moment form, and then the update in the information form, the information filter. We could do that, but unfortunately, the cost of converting between both representations also the most expensive cost of the individual operations. Okay, so we can argue that it's depending on what we need. The information filter may be better, or the extended Kalman filter may be better, or the Kalman filter may be better. And especially we'll see for the context of the simultaneous localization mapping problem, if I apply the vanilla extended information filter, I don't gain anything. I even typically make it worse because, if we go back, so here the cubic complexity was mainly in the dimensionality of the measurement function, and here it's the dimensionality of the whole state space. So if I observe only a small part of the landmarks at the same time, the EKF is even more efficient. However, as we will show next week, there are opportunities for introducing some approximations and then making the process efficient. Okay, if you want to go from the what we did so far, we transformed the Kalman filter into the information filter. Now we want to do the same thing for the extended Kalman filter, moving from the extended Kalman filter to the extended information filter. Now this is done in a rather straightforward way. So we use exactly the same tricks that we did before to transform the KF to the IF, or the EKF to the EIF. So we use exactly the same Jacobians as we did before for linearization. So we have our function g, it's a function g evaluated at the mean, and then the Jacobians measuring the difference to the mean is the same thing for the measurement functions. So exactly the same way as we did that for the extended Kalman filter. And if we look, if we simply substitute so we use the things we use the EKF to substitute this equation to come to the information form. So we start with the covariance matrix. So this was G, the covariance matrix of the previous times that G transpose plus RT, and this ends up in GT, the inverse of the information matrix, GT plus RT to the power of -1. So exactly the same kind of direct character replacement operations as we did for the Kalman filter. And the information vector here is information matrix times, and now we have the problem at that point that this function g is only defined in the state space. So in the space where we also use the define the probabilities, so the variable x we investigate. So we have to transform at this point the information vector into the mean estimate in order to be able to propagate it through the nonlinear function. At least if we have the nonlinear function given in that way. If you only have the kind of regular g function which works on x and not on the information vector, we have to kind of convert that back to the mean, so recover the original state space, propagate it to g, and then convert it back. That's kind of potentially suboptimal. So if we do that from the extended Kalman filter to the extended information filter, these two lines get replaced by these lines. So first, we kind of have to recover the mean, then we compute the covariance matrix, and then we compute the prediction of the mean, and then turn it back into information form. Because currently our function g is only defined in moment form. The correction step can be done exactly in the same way as we did it before, going from the Kalman filter to the information filter. We can now go from the extended Kalman filter to the extended information filter. So our belief looks like this function over here. So we have the we don't have zt minus capital C x, which was a linear function we had in the Kalman filter. We now have the linearized nonlinear function in here, same in here, and the previous belief. And this leads to, we do exactly the same steps as we did before, and we end up in this form over here. So we have the Jacobians of the measurement function here and computing the new information matrix, and the same update in here for the information form. But again, this involves no new inversions or something like this. So the update step still maintains the efficient in the extended information filter, and the prediction step still is the costly one for in the extended information filter. So we sum that up into an algorithm. So this was kind of the first line 2 to 5 was the prediction step, and these 2 lines are the correction step. Again, the thing which is a bit weird here is that we here first have to leave the information form, go to the moment form in order to recover the motion, the motion update, and then turn back to information form, and then continue with the rest of the algorithm. But in theory, we can apply that algorithm, replace the Kalman filter by the information filter, and operate completely in information form. The results we obtain are the same in terms of the estimates we obtain. Maybe more costly to do that in the information form, especially if as the measurement update in the EKF has the qubit complexity only on the landmarks that can be seen at the same time on the measurement dimensionality of the measurement function, and not on the full state space, where the information filter has here these inversions, which requires an inversion of this 2n plus 3-dimensional matrix, which is in most applications or most realistic SLAM settings the more costly operation. So if we look to the EKF versus the extended information filter versus the extended Kalman filter. So I said the EIF, the EKF in information form. What the one can do efficiently is slow for the other one, the other way around. We don't. Question is, do we gain anything? And in the end, in the practice, is the EKF, especially if you go to high-dimensional spaces, is often more efficient than the EIF, at least if it's used as a kind of plain algorithm that I presented in here. So there are a couple of approximations which try to fix certain issues or circumvent certain problems that one had. But at least in the form I presented it here, typically the EKF is more efficient than the EIF and also more popularly used, especially in the context of the SLAM problem. However, the extended information filter is typically numerically somewhat more stable than the extended information filter, at least that's what you find in the literature. But the both have the same expressiveness, so mathematically they do exactly the same thing. Well, the only one in information form, the other one in the moment form. And we could use the unscented transform we used before, and could also put it into the information filter. There are also unscented information filters, but that's nothing we are going to look into here. So what should be kind of the take-home message from this lecture here on the extended information filter? First, Gaussians can be represented in 2 ways, moment form and in the canonical representation. They are both equivalent in terms of the probability distribution they represent. Converting between one representation to the other representation requires inverting the matrix with the dimensionality of the problem. So this is a costly operation. And the Kalman filter is efficient in the prediction and slow in the correction, and the information filter is exactly the other way around. It's slow in the prediction and efficient in the correction step. And the application that we have determines which is superior to respect to the other. So there, for example, multi-robot settings, so you have multiple robots sending information around, and these information can be typically more easily integrated into this information form, because you have multiple sources, you can just add them up in these multiple sources, which is a very nice property, and therefore, especially if you go to multi-word context, the theory, these information filters have advantages, especially if you look to the approximations of the information filters, sparse extended information filters. If we look into sparse extended information filters line next week, then we can actually gain advantages from operating in this information.